Okay, so what is this checkpoint about? I also need to recall. Okay, so basically what we are doing here is we are trying to mix two soluble salt together and see whether it causes precipitation. Okay, so at the instance of mixing, we need to calculate what is the ionic product to check whether it's equal or exceed the Ksp. So if it exceeds the Ksp, then precipitation will take place. If it doesn't, then it will just be a saturated solution or less than saturation. Okay, so when you add equal volume of the soluble salt together, what is it that you need to consider? What is it that you need to be careful of? Yeah, there will be dilution. So part B is actually even more straightforward because you are told that it's equal volume. So once you have equal volume added to each other, what will happen to the dilution? Oh, the answer is already given. I don't know why they tell you all this for what. Okay, anyway. It's already given, then what is there to calculate? Eh? Is it yours or is it just mine? Yeah, so is there. The answer is staring at you. Yeah, what? Yeah, this is a what? I also don't know what. Okay, so quite straightforward, right? The concentration of the chloride, which is coming from hydrochloric acid, it will be 0.1, half of the original. Then the silver nitrate, the concentration upon mixing will be half of the original, 0.005. After which, you need to substitute into the ionic product expression, which is the same as your Ksp expression. Okay, so this is the instantaneous value of your ionic product. And after you have obtained this value, you need to compare it with the Ksp. So what can you conclude from here? When you compare with the Ksp, what does it mean? What's the significance? Yeah, it's larger. So if it's larger, what does it mean? Yeah, it will undergo precipitation. So it will keep on pushing out your silver chloride until the ionic product becomes Ksp. Why need to copy? You know already, right? Oh, sorry. Do you understand this part? Precipitation occurs until ionic product equals to Ksp. Do you know what it means? The value is the same. So what's the significance of ionic product equals to Ksp? Yeah, the solution is saturated. All right, it's already carrying the maximum amount of ions. Okay, so carrying the maximum amount is not going to push out anymore. All right, it's comfortable with this maximum amount. Okay, so this is when the new POE is achieved. New POE is achieved. POE is achieved. There's no new POE. When POE, when equilibrium is achieved, sorry. When equilibrium is achieved, your ionic product will be equals to Ksp. Okay, let's look at the next part. So far, so good. Okay, the next part is the more difficult part. Okay, we are doing selective precipitation. Okay, and you're going to see the real life application when you do inorganic QA unknown next week. All right, so next week, Thursday, you'll still be doing practical. All right, but then someone else will relieve my class. Okay, so tomorrow I will go through all the thinking process required. Then when you do the Thursday practical, you know what you're doing. If not, right, blah, blah, don't know what's happening. Okay, so please take note. Selective precipitation is only applicable if you have a mixture of ions. Mixture of ions. That's why there's a need to separate them physically. Okay, so if there's only one ion, no need to carry out selective precipitation. Okay, it's because there's more than one, then you need to physically separate them. And what do I mean by physically separate them? I have to physically separate them by carrying out a filtration. So one ion will be captured as a residue on the filter paper. The other ion will flow through as a dissolved solution as filtrate. Okay, so that's how we physically separate them. Okay, so let's try to look at work example 7. So work example 7, you have 25 degrees Celsius. At 25 degrees Celsius, your silver plus is of 1 times 10 minus 2, while the lead 2 plus is 2 times 10 minus 2. Okay, then obviously silver plus and lead 2 plus will form a sparingly soluble solid with the chloride that is introduced through the sodium chloride. Okay, so you need to recognize that sodium chloride over here is a soluble salt. It's a source of chloride and is a fully soluble salt. Okay, so as you add the sodium chloride salt bit by bit to this mixture, you are going to expect precipitation of one of them, leaving the other still in solution. Okay, so that is the purpose of selective precipitation. So my first question is, can I infer relative solubility of silver chloride and lead chloride from their Ksp value? Can I just infer from Ksp value? No, why not? Yes, so in this case, the ratio is not the same. For silver chloride, the ratio is 1:1, while that of lead chloride, the ratio is 1:2. So whenever the ratio of cation to anion is not the same, then I cannot infer solubility from Ksp value. Okay, which means that I need to calculate their solubility instead in order to deduce the relative solubility strength, solubility in water. Can? Okay, so if you look at the next part over here, can so far? Sorry, I'm a bit fast. Okay, so let's look at this. What do you think is the purpose of calculating this? So from the first calculation, we know the minimum concentration of chloride required to precipitate my silver chloride is 10 minus 10. While that for precipitation of lead chloride is 10 minus 2. Okay, so can you tell me, 10 minus 8, sorry. 10 minus 8 and 10 minus 2 respectively, right? So what is the significance of this value? What is it trying to tell me? Yeah, so as you add your sodium chloride solid progressively to this mixture, who is going to precipitate out first? Silver chloride, because it will reach the threshold faster, right? So the minimum concentration of chloride here is like a threshold. You hit that threshold, it will start to precipitate. Okay, so the threshold is indeed much lower for silver chloride than lead chloride. Okay, so this means that my silver chloride will be precipitated first. Okay, so this is what the question is trying to tell you. So from here, are we able to prove by calculation that silver plus is effectively separated from lead 2 plus? Can we prove by calculation? And how do we do that? So before we do that, right, there's this diagram that is printed on your lecture notes. Okay, so can you help me revamp that diagram to this? Yeah, revamp. Okay, okay, now you copy this down. The whole thing. Yes, the whole thing. So if you understand, then no need to copy the whole thing, I think. I only product. Copy the whole thing. If you have your tablet, then you can just take a picture. But most of you don't work with your tablet. Yeah, so. Not the same. Because green is associated with when silver chloride is about to precipitate. When lead chloride is about to precipitate. Yeah, the orange one is before precipitation. Yeah. None of you are colorblind. Hmm? Who? The person is colorblind? Huh? You're colorblind, then you did not alert us. You have A, then all along chemistry, you have not been asking for help, eh? Hmm? Yeah, but still there are certain colors that you cannot see, right? So are you able to see the green and orange? Oh, so not so bad lah. So what is the color that you cannot see? Red, green. The help that is rendered, right? You must still tell me, is this color? Then I say yes or no only. Yeah. That is for titration. That's for titration. But if it's a QA, then I need to tell you the color. So you just apply for A this year. After you're done with copying, can you try to fill in the blanks? That is the whole process. So in order to understand the whole process, you must recognize that the ionic product will keep on changing. Okay, once you're done, right, you can discuss with your elbow partner first. Yep. Yep. Yeah. So at that instance, when your sodium chloride is progressively added to it, it will always exceed ionic product. Yeah. So only silver chloride precipitated is because once you add chloride, it will be beyond Ksp. Yeah, so before equilibrium, it will exceed. At equilibrium, it will become equal. At the moment whereby you add in a little bit more of sodium chloride, the ionic product will exceed Ksp. That is when the system will push silver chloride out. So before you add in another bit, it will attain equilibrium, right? So at equilibrium, ionic product of silver chloride will be equal to Ksp. So that is at equilibrium. Yep. Yeah. But then, no, it's not past equilibrium. So it will push out more. The moment, it will go back to equilibrium. That's the meaning of new POE attained. New POE is always attained with every bit of sodium chloride added. Yeah, it's always an equilibrium. There will always be silver plus remaining. But what we want to prove is what remains is negligible. What remains is negligible, therefore it's an effective separation. Yep. Fill in the blanks. Huh? What? I don't know. Yep. Oh no, what I'm trying to say is when you only see silver chloride being precipitated is the moment you add sodium chloride, ionic product will exceed Ksp. Before you add in another bit of sodium chloride, is allowed to reach equilibrium. So with every bit you add in, newly added in, right? Ionic product will exceed Ksp of silver chloride only. That's why only silver chloride precipitates out. So when it reach equilibrium, ionic product will become equal to Ksp before you add in another bit of sodium chloride. Then it will become equal. Yeah, so before equilibrium is attained, it must exceed in order to precipitate. Yeah. Then after it precipitate is comfortable at equilibrium, new POE, then it will become equal. Yeah. Okay. Yep. Oh, because initially, right, your silver chloride silver plus and chloride minus, right? So let's say at this moment, my ionic product exceeds Ksp. So this means that my precipitation will take place. Okay, so when precipitation takes place, then it will start pushing out silver chloride. Then this will decrease, right? So when these two decrease, it will not decrease for ionic product to become lower because it has already exceeded saturation point. So as it pushes the solid out, it will reach a new position of equilibrium when this product is just right at saturation point. When ionic product is equals to Ksp, the solution is saturated. Yeah, but it cannot go to become diluted because there's already PPT push out. Haven't filtered out yet because I've not maximized the precipitation of silver plus yet. I have not started filtration yet. I have to keep on adding, keep on spamming to make sure that majority of silver plus is precipitated first before I can separate. I cannot just, once I see PPT, I will filter. Huh? Cannot shift now. You already removed the solid, how to shift? In order for POE to shift, the reactant and the product must be present because it's an equilibrium, right? So once you remove the solid, how to shift in POE? Nothing to shift. No, your solid is constant concentration. After you remove it, right, the POE cannot shift anymore. Am I making sense? Okay, so let's fill in the blanks. So let's look at the footnote at the bottom. So Ksp of silver chloride and lead chloride will remain unchanged throughout. Okay, because it's only affected by temperature. So since temperature is held constant, the big letter K unchanged. Okay, but then you must recognize that the position of equilibrium can shift as the concentration of ions changes. So POE can change. And POE changes, this means that the ionic product will also change. Okay, at the moment of disturbance. Okay, so I emphasize the ionic product can change at the moment of disturbance. When you add in fresh bit of sodium chloride, ionic product will change at that instance. Okay, so at that instance, once your ionic product exceeds Ksp, then it will cause precipitation to take place. Okay, the instance you add in sodium chloride, ionic product exceeds Ksp, it will cause precipitation. That's the rule. Okay, so it will precipitate until ionic product equals to Ksp again. That is when it will stop to precipitate more. Okay, so at equilibrium, ionic product will be equals to Ksp. Okay. Okay, so this diagram, right? What is happening in this diagram is you have 0 of the sodium chloride added. Okay, before you add in any sodium chloride, okay, or as you progressively add in more, it will take some time to exceed the ionic product. So before any precipitation takes place, you are very sure that the ionic product for both is lower than their corresponding Ksp. Therefore, you observe no precipitation as a result. Okay, so it's not high enough to exceed Ksp. Okay, but as you add more bit by bit, it can hit the minimum concentration for chloride, silver chloride to precipitate out. Okay, so the moment silver chloride is about to precipitate, we must recognize that the ionic product must be equal to Ksp first. When it's about, meaning haven't precipitated out yet, it's about to precipitate. So the ionic product must be equal to Ksp. And at this moment, the ionic product of lead chloride is still lesser than the corresponding Ksp. Not high enough. Okay, so what happens the moment you add in a little bit more? Okay, so because your silver chloride has reached saturation, so the moment you add in a little bit more of sodium chloride, what will happen? At that instance, the ionic product will exceed Ksp. At that instance. So this means that precipitation will start to take place. So at that instantaneous, it exceeds, precipitation start taking place. Okay, so before you add in another bit of sodium chloride, when it attains equilibrium, it will become equal again. So this is before you add in another bit of sodium chloride. Okay, so of course, at this moment, ionic product of lead chloride is still less than Ksp. Okay, now I'm going to paint a scenario now. I need you to recognize that as silver chloride is being precipitated, what will happen to the silver plus remaining in the solution? As silver chloride is progressively being precipitated, what will happen to the silver plus aqueous? It will decrease. So when the silver plus aqueous decreases, it allows the chloride aqueous to increase in concentration. Agreed? because you have less silver plus present to precipitate, right? So it allows the chloride concentration to climb. And when the chloride concentration starts to climb, the moment it hits the ionic product of lead chloride, then you should stop adding your sodium chloride. Understand? Okay, so the moment your lead chloride is about to precipitate, okay, the ionic product must be equal to Ksp. Okay, and at this moment, when equilibrium is attained, ionic product of silver chloride also equals to Ksp. So do I want to continue adding sodium chloride? Do I want to continue adding sodium chloride? Do I want to go beyond this point? No, because once I add in another bit of sodium chloride, what will happen? My ionic product of lead chloride will exceed Ksp. Then my lead chloride will start to precipitate as well. Okay, so at this moment, right, I can no longer add sodium chloride. I should stop. Can? So from here onwards, right, stop adding. Yep. Because it's at equilibrium with its solid. They are equal for different reasons. The aqueous solution of silver chloride is still in equilibrium with silver chloride solid because you haven't carried out any filtration yet. They are at equilibrium. So that's why I put at equilibrium. That means it's after the disturbance. Yeah. Okay, so at that moment, the ionic product of lead chloride is also equals to Ksp. Yeah, because that will be the maximum concentration of chloride required to cause maximum silver plus precipitated. What is it? Yeah. Must exceed first so that it can become equal. Yeah. So that means at equilibrium, the POE doesn't shift anymore. So at that moment, right, the ionic product of silver chloride must be equal to Ksp. The POE is fixed now. That means it has already responded to the disturbance. So when I say at equilibrium here, right, it's a new position of equilibrium. It's different from at equilibrium here. No, you must imagine it to be, you are adding sodium chloride bit by bit. Okay, so every bit you add, right, it will cause a disturbance. Agree? So if this disturbance causes the ionic product of silver chloride to exceed, then only silver chloride will be pushed out of the solution. Precipitate lah. Okay, so when does it stop precipitation? When the ionic product equals to Ksp. Yeah. So that is at equilibrium. Then when you add in another bit, then you cause a disturbance again. Then the whole story again, go one round. So it's a repeated cycle until you reach the saturation point of lead chloride. Yeah. Anyone who is not following? Yeah. Position doesn't change, the position change. POE change, yeah. Yeah. POE can only change in response to LCP. Concentration of chloride changes as you add in your sodium chloride bit by bit. Precipitation. Because you pump in more chloride, right? So it will push more solid out. Yeah. Ionic product aciding Ksp means that it has go beyond its saturation point. Yep. So that is the maximum amount. If once you go beyond that, your lead chloride will precipitate also. And you don't want that to happen. Because the idea here is to separate the two cations. You don't want both of them to be in solution. Yeah. Yeah. Because you want to separate them, one in solution, one in solid. If you go beyond this point, your lead chloride will become solid as well. Then you end up with a mixture again. Make sense? Yeah. Okay. All right. So in this case, this is what is happening. All right. So how do we prove using calculation that silver plus is effectively removed from the solution or physically separated from lead 2 plus? How do we prove that? Huh? Yeah, final over initial concentration. So, but then the thing is, right, how do I determine the silver plus aqueous that remains in the solution? How do we determine that? Okay, so recognize this point. This is a very important point. When you have maximum pure silver chloride precipitated, this is also corresponding to lead chloride about to precipitate. At that moment, please take note, ionic product equals to Ksp for both solid. This is very important. All right, so this means that I can equate concentration of silver plus chloride to be equals to the Ksp value, right? So my lead 2 plus and chloride ionic product equals to Ksp value. So let's check. Do I know what is the silver plus left behind after precipitation? Do I know this? Okay, this is a question mark. I don't know. Okay, this is given to me. I know. This is also given to me. I know. All right. So this, do I know this? How? The maximum point. So what is the maximum point? How do I calculate this so-called maximum chloride that maximize precipitation of silver plus? Yeah. Why do I use Ksp of lead chloride? Why? Huh? Go back to the same point, meaning both at the same point. Now, so it goes back at the same Ksp point. Okay, so in other words, right, you must recognize that this is very important. Your lead chloride is about to precipitate. So this means that when it's about to precipitate, is any of your lead 2 plus precipitated? No. Then do you know the concentration of this? What is the concentration of lead 2 plus according to the question? Done. Yeah. So if this is given and none precipitated out yet at that moment, I know the Ksp value of lead chloride. Can I calculate what is this? Yeah. And this is communal. Yeah, it's shared by the two sparingly soluble salts since they are swimming together in the same solution. So when I calculate chloride concentration from here, it will belong to both the salts. So far, so good? Yeah. So chloride can then be substituted back to the Ksp of silver chloride to get the silver plus remaining in solution. Okay, so this is unknown, but we can work backwards. Okay, by looking at what is chloride, how much of chloride is present in the solution first. And we can work backwards from the more soluble solute. Okay, so this is exactly what is happening. If you look at this working, this is the concentration of chloride derived from equal to Ksp lead chloride. Yeah, this is actually above. Remember, you have done this. This is the original concentration of lead 2 plus. This is the chloride minimum required to cause precipitation. Yeah, so this is communal at that point of time. So you substitute this concentration back and equate it to silver chloride Ksp. Then you can find out how much of silver plus still remain in solution. Yeah, so with this calculation, like what Yuelin has said, I look at what is left, I look at what is original, I can calculate the percentage. Then you can see that it's 10 minus 5 is negligible. So what remains at that point of time is negligible, therefore it's an effective separation. Ken? Okay, so if you have understood this, right, you can proceed to checkpoint 5. Ah, 10 minus 5 is very negligible. No lah, we will not give you something ambiguous. It will be a good enough difference. Yeah. So if you have no further question from this, right, can you do checkpoint 5 now? Okay, as you are doing checkpoint 5, you also have things to copy. I mean, if you understand what's going on, don't need to copy this. So basically, you notice that nowadays, right, I keep giving you this kind of paragraph. So it's to make sure that conceptually you are there. Correct. Accuracy. Okay, so after you have calculated here, or you should look at this first, then you do your calculation, either or, up to you. So this will check your understanding. Sheng Hao okay or not? Yeah. Huh? Next product. PPT is debated. To determine. Before I forget, some of you never hand in your inorganic booklet. Okay, so remember to bring it tomorrow. because I'll be using it to teach the thinking process. So remember to bring it tomorrow if you have not submitted. Okay, so you manage to calculate? Is the numerical answer already provided? Huh? Is the magnesium carbonate? If I erase something. Oh, yeah. So there's numerical answer provided. So are you able to get the answer? Yeah, they are the same. Is the shouldn't be the same or the same? Okay, so shall we look at the paragraph first? So from the comparison of Ksp of magnesium carbonate and lead carbonate, which one is higher, which one is lower? Magnesium carbonate is higher, right? And in this case, we can already infer their solubility trend because the cation to anion is 1:1, both. So this will imply that who will precipitate out first? Lead carbonate will precipitate out first. Okay, so since no magnesium 2 plus precipitated, then magnesium 2 plus will still be 0.01 mole per dm cube. Then we should use Ksp of magnesium carbonate to determine the carbonate maximum required to maximize precipitation of lead carbonate. Yes. Okay, and that will avoid, at the same time, to avoid precipitation of magnesium carbonate. Okay, so please take note when new POE is attained, ionic product must be equals to Ksp. Yeah, so this is the explanation behind, right? So the calculation will just be this. That's it. I will not show the rest. Why is it 10 minus 12? But why do you need to calculate that? But the main question stem never asked what? The main question stem is only asking, calculate the concentration of carbonate to precipitate only lead carbonate, but not magnesium carbonate. Yeah, that's why I blank it out. I blanco it blue. It's not answering the question. Again, sorry. Did I set this textbook? No, I didn't set this notes. They never asked me to vet what. We vet each other. We are working in pairs. Yeah, as in the organic booklet, right? I'm in charge of certain topics. Then the other teacher will vet. Then we vet each other. So some teachers will be in charge of this equilibrium. Yeah. So we don't work with the whole thing. Yeah. If I work with the whole thing, it will kill me already. I'm the one who designed the whole practical series, you know. Yeah. No, because I'm the practical coordinator, so I prepare that. Yeah. I mean, it's not from scratch, but I do some revision here and there. Okay. Okay, so we are done here. So let's move on to the next part. Okay, so this part is the application of Le Chatelier principle. We are going to look at how we apply LCP with respect to this sparingly soluble salt system. Okay, so let's quickly look at this work example here on page 14. Okay, so I'll just bring you through. So silver chloride is the sparingly soluble salt system that we are looking at. Okay, so do recognize that hydrochloric acid is a strong acid. So it will undergo full dissociation. So it's a surplus of chloride here. There's a surplus of chloride coming from hydrochloric acid. So because of this surplus, it will cause a disturbance to your equilibrium number 2. There's a disturbance to your equilibrium. So how to respond to this disturbance? According to Le Chatelier principle, to partially offset the increase, it will favor the left side of equilibrium 2. Or you can say that it will shift left to react aqueous chloride away. Or you can say precipitation of silver chloride is favored. There are many ways of talking about it. So it depends on which way you like. All right. So if you want to say shift left, shift right, you have to write the equation there so that I know what it meant to shift left or right. Okay. If you did not have the equation, then you just tell me the process that is being favored. Make sense? Okay, you digest a little bit. Okay, so according to equilibrium number 2, forward direction, you describe it as dissolution. You are trying to dissolve your solid. Then the backward direction is known as precipitation. Okay, so with a surplus of chloride, it will favor the backward, which is also precipitation process. So if you don't want to learn these chim words, then you just write the equation, tell me shift left or right, that will do. Okay, can? Now there's another way of discussing it that will be talking about ionic product and Ksp. This is also acceptable. This is also acceptable. But I find that most students will prefer the Chatelier principle because they can apply to all equilibrium. Can? Right, so it's really up to you. Which one you are more comfortable, you just use it. Okay, next, work example 9. So far, so good. Okay, so let's look at work example number 9. So work example 9 is divided into 2 parts. Part A, you are asked to determine solubility in pure water. Part B, you are asked to determine solubility in sodium chloride solution. Okay, so there's a difference here. All right, so the moment the question asks you for solubility, please recognize that the solution has to be saturated. When I bring in the term solubility, right, the solution must be saturated in the first place. So this means that my ionic product must be equal to Ksp. Okay, and that is the chemistry principle used for all this calculation. Again, sorry. Why? Why doesn't it hear anything? It's the same thing, eh? No? How to check? Yeah, it's the same method. Yeah, so where is the audio? It's not muted, huh? Hello? Yeah, weird. It's just weird. Yeah. laptop. I off the audio here. If not, there'll be a lot of echo. No, it's the same method when I go there and do it. Yeah, so it's exactly the same. All right, let's come back to this. All right, so let's look at the ice table. Ice table over here, right? Some of you may think, hey, why so redundant? I put 0 here and 0 here. Okay, so the significance of this 2 0, right, is telling you that before the silver chloride starts to dissolve, you have no other sources of silver plus and chloride minus. That's the meaning of the 2 0 here. Okay, so initially, right, before your solid starts to dissolve, there's no silver plus, no chloride present. That's the meaning of the 2 0 here. Okay, then when your solid starts to dissolve, this is the solubility. So the part that is dissolved will form 1s of your silver plus, 1s of your chloride. So therefore, at equilibrium, this will be the corresponding concentration of your silver chloride in this saturated solution. So S square, just square root, get the answer. Straightforward. Okay, so this one is provided in pure water, but it becomes different when it comes to part B. Okay, let's zoom in on the initial part again. Initial part, you are adding or you are trying to calculate solubility of silver chloride in sodium chloride solution. So appreciate that before your silver chloride starts to dissolve, there's already chloride from sodium chloride. So there is other sources of chloride present in this mixture. Okay, that's why you have 0.1 there. Okay, silver plus is still coming from your sparingly soluble solid, has not taken place yet. Okay, so 0. Right, next, when your silver chloride starts to dissolve, then you will have 1s prime of the silver plus, 1s prime of the Cr minus. Then you add them up to get the, concentration at equilibrium. Make sense? Who's lost? Okay, this one is very important because A level like to ask solubility of a solid in something else. Okay, so you need to appreciate that if there are other sources of ion common to your sparingly soluble solid, then your ICE, the I, will change. Okay, so you must understand the significance of that. 0.5? No. Okay, so why do I give it an S prime here? Why not continue to use S? Previously, we are talking about solubility of silver chloride. Here, also solubility of silver chloride, right? So why don't I just use the symbol S? Why must I change from S to S prime? Because the value has changed. So how do you think the value has changed? Smaller or bigger? Smaller, because of Le Chatelier principle. The presence of surplus of chloride makes the solubility even smaller. So that's why it becomes an S prime here. Yeah, and in this case, right, if you talk about concentration of chloride, you must recognize that the chloride comes from two sources, coming from silver chloride as well as your sodium chloride. While the silver plus only comes from your silver chloride. Okay, I need you to recognize this. Then after which, right, you have to know that since this is sparingly soluble, the solubility will drop. So this becomes negligible. The contribution by your silver chloride becomes negligible. Therefore, when you substitute this in, right, this is totally coming from your sodium chloride. Just like strong acid suppresses a weak acid. This is a fully soluble salt suppressing the sparingly soluble salt. Okay, so the chloride will come solely from the fully soluble salt, negligible from your silver chloride. Can? Right? So you substitute this in and get the answer to your silver plus. And this answer will be your S prime. It will still dissociate because it's always an equilibrium. It's always an equilibrium. Yeah. So it's a matter of how the POE shift. The Chatelier principle. Yeah. So it must still be an equilibrium. Yeah, insignificant now, so we can just take it to be sodium chloride. Added them, but it will be negligible anyways. It's just an additional step. Well, but you must remember that there's chloride coming from sodium chloride. So students most often will forget sodium chloride. They will not forget silver chloride. They will forget sodium chloride instead. Yeah. So that is not a major mistake. Yeah, major mistake is ignore sodium chloride presence. Yes? Significant meaning? Insignificant. Because the original solubility is already 10 minus 5. What? So in the presence of sodium chloride, it will become even less because of the Chatelier principle. 10 minus 5 is already negligible. Yeah, go towards precipitation. So 10 minus 5 is already negligible compared to 0.1. Yeah, so you can justify that. Okay, let's practice using this. Can we quickly practice? Determine the new solubility of silver chloride when it's dissolved here. This one, A-level question always come out. So practice now. I only have half an hour more. Less than half an hour. I need to finish this topic. Yeah. I don't memorize the answer. Okay, so the idea here is your silver plus is only coming from your silver chloride, but your chloride minus is coming from silver chloride as well as AlCl3. But we know that this is negligible. Okay, so it's equals to 2.0 times 10 minus 10. So now what is this concentration? That's the crucial one. 0.6. Okay, so you have to recognize that this fully soluble salt gives you 1:3 ratio of chloride. Okay, so this will be times 3 of this, 0.6. Then you substitute inside the expression to calculate the concentration of silver plus, and that will correspond to your solubility. Because silver plus only coming from silver chloride, right? The silver plus only comes from your silver chloride. So whatever silver plus you have must be dissolved from silver chloride. That's why the concentration is equal to solubility. Okay, so what's the answer again? 3.33 times 10 minus 8, is it? Minus 10. Huh? Huh? Necessary? No, if you can skip the IC, by all means skip it. Yeah. If you don't need to go through it, you can see it straight away, skip it. Doesn't matter. Yeah, IC is more for people who needs a more systematic thinking. Yeah. So if you don't need it, by all means skip it. Okay, the next thing I want to go over is this part. So I need you to copy again. Huh? Copy again. Yeah, copy, come. After you're done with this copying, then you can read the subsequent pages. Copy your notes off. Read it, okay, read it on. Yeah, you read it, can, doesn't matter. This part here, right, is very related to your inorganic QA. Very much related. No voice, no voice. Dying. Huh? Okay, what? Is it? I don't know. I just feel that I cannot get my message across. Huh? Yeah, I have OCD. Hello? The sequence placed here is different from the organization of the notes. So if you're not copying, right, you can look at the different pages. As usual, you can just take a picture. The one. Huh? Play sheet? It's not play sheet. It's actually more efficient. I would have preferred you take picture, then I can continue. Huh? Yeah, true. But some people can only do one thing at one time. But if you do econs paper, you also need to write a lot, right? I thought strong conjugate base of acid-base equilibrium. Yep. Yes. Yeah, you can't find it because I put it under teacher only. Yeah, but because when I step in this classroom, I say some students don't know how to do chemistry, but IT very takong. So they go and copy my notes and got all the answer because I just blanco, right? They can actually copy and paste somewhere else and get all the answers. You can still do that for teacher only. Huh? Why? How? Meaning? You mean under teacher session you can still see, man? Teacher only, leh. Yeah. Yeah, the rest I don't know, ma. That is before I'm innocent. Now I already know. That's why this is under teacher session. Yeah, nowhere else. So you cannot see, right? Confirm but short, right? Cannot see, right? This one? Yeah. Then I'm safe. Yeah, sorry. Yeah. Then I have to duplicate many versions. Wow, that's very challenging. Because I keep on looking at it, I keep making changes. Then I have to change all over the place. Then until I'm very confused. That's the problem. Yeah. It's not that I prepare something, you can sit there for a long, long time. I keep on looking at it. Okay. Yeah. Anyways, IDC. Okay, are you done? Yeah. So let's look at this. Number 2 is what is already familiar to you. So basically, number 2 is talking about common ion effect. Okay. So as a common ion, it will suppress the solubility of your sparingly soluble salt. So it will favor precipitation process. So this common ion can come in the form of cation or anion. So with surplus of this cation or that anion, it will cause backward process to be favored. That's why less can become soluble. Okay, so that is what we have talked about already. So the first one is something new to you. Somewhat new, but not exactly new. All right, so for first one, you need to check for possibility of forming a soluble complex ion. Okay, and the formation of this complex ion causes the concentration of your cation to drop. And because the concentration of cation drops, that's why it will favor the forward dissolution process. Okay, so if you look at what you have done under QA, inorganic QA, let's look at the QA notes. Okay, under this QA notes table, when you have sodium hydroxide as a reagent, okay, notice that you form a lot of different PPT, right? So this PPT can be formed because they are all sparingly soluble. Yeah, they are all sparingly soluble. That's why they can be formed. Yeah, they exceed Ksp, right? The ionic product exceeds Ksp, therefore it forms the PPT. And notice that there are some PPT that are formed that dissolves in excess of sodium hydroxide. One example will be Al3+. This is the sparingly soluble solid, which is aluminum hydroxide. Then with excess of sodium hydroxide, it becomes soluble. So the moment it becomes soluble, it implies the formation of the complex ion. Remember, I introduced this to you, AlOH4 minus. This is inside your inorganic QA booklet. This is the soluble complex. Why is this called a soluble complex? Because it carries a charge. It can undergo favorable ion dipole interaction with your water. So this is soluble. Okay, so if you look at another example, chromium 3+, it also forms a PPT and it becomes soluble in excess of sodium hydroxide. So this is also due to formation of this chromium soluble complex, 3-. Okay, so if you look at another example, here, your zinc 2+. Zinc 2+ also forms a what PPT, zinc hydroxide, and soluble in excess. So this is also due to formation of zinc hydroxide. Does this ring a bell? Yeah. So these are all formed due to the excess of sodium hydroxide. These are your soluble complex. Okay. So being your metal hydroxide, this OH minus here is the N ion. N ion. So when this N ion is given in excess, it can cause soluble complex to be formed, which enhances the solubility of your PPT. Okay? Right, so these are the three. Okay, so this is the example whereby you spam the anion, same anion added, it results in the formation of soluble complex ion, and the formation of which causes the cation concentration to decrease. Okay, as a result, it will favor dissolution. Okay, so since the anion is the same, right, there could be two effects. One is common ion effect, which will reduce the solubility. But once you saw that the question implies enhanced solubility, then you must recognize that it is forming a soluble complex. Okay, I repeat myself. Adding surplus of the same anion, there are two possible scenarios. The first possible scenario is exerting a common ion effect, which will reduce the solubility. Okay, like what you see in example number 2. Silver chloride with surplus of chloride. Okay, but do recognize that the anion, if added in large excess, can also possibly result in formation of a soluble complex. Okay, so that will give rise to enhanced solubility. Okay, so you have to read the question to know what they are driving at, to answer to the question. Okay, so there's this clause over here. A soluble complex can also be formed with aqueous ammonia. So this is also metal hydroxide being sparingly soluble. Okay, but with excess of ammonia, it can form a soluble complex with ammonia that enhances the solubility. For example, if you look at your QA notes, under the section ammonia aqueous. So if you look through the whole column, right, you will see this instance, copper hydroxide PPT form, soluble in excess to form dark blue solution. Okay, so this is the instance whereby your copper forms a soluble complex with excess ammonia, which will reduce the cation concentration, hence favor dissolution. Yeah. Okay. So this is one instance. Another instance is this part, your zinc. White PPT, soluble in excess. So this is also due to the formation of ammonia complex. This one you have to know. You have to know. Okay. So the number of ammonia or OH minus attached is generally twice the charge. Okay, I repeat myself. The number of ammonia or hydroxide attached to form this soluble complex is usually twice the charge. For example, zinc 2 plus. So twice of it is 4. So a net charge of 2 minus. 2 plus, twice of it is 4. But ammonia is neutral, charge neutral. So it assumes the cation charge. Okay? Right? So if you look at the case of chromium, chromium is a 3 plus. So twice of it is 6. So 6 minus 3 plus, net charge of 3 minus. Okay? Right? So generally that's the trend, except for this one. This is the exception. Remember, I've gone through this review during the inorganic QA. Yeah. Okay. So what I'm trying to say is there's no need for you to memorize what can form complex, what cannot form complex. You can refer to this table and infer from there. Yeah, but you must recognize the complex form is different when it's excess sodium hydroxide versus excess ammonia. Okay, so take note of the difference. Right, so let's quickly look at checkpoint 6. Okay, so it's on page 17. Yeah. Okay, so this is an example of complex formation now. So you read yourself, can? Read yourself, huh? So this work example here. Okay, so shall we look at work example 12 first? So notice that there's an equilibrium here due to your weak base. There's also an equilibrium due to your copper hydroxide. Okay, another equilibrium that forms the dark blue solution. Okay, so there's a lot of equilibrium in this mixture. Okay, all right. Now, can you predict what will happen if I add H plus to the deep blue solution? What do you think will happen? Disperse, meaning? You will react with the OH minus. So which OH minus? There's two sources of OH minus. OH minus from your weak base, OH minus dissolved from your copper hydroxide. Why dissolving? Why not hydroxide from your weak base? Now, okay, so what is going to happen here? Please take note, it will cause reprecipitation of copper hydroxide. This will definitely take place. It will cause the copper hydroxide to come out again, okay, when reacted with acid. So if this is true, which hydroxide must it react away? If we are going to see reprecipitation of copper hydroxide, right? So which hydroxide should be reacted away? Second one. If it's the second one, then your copper hydroxide will dissolve. Where got reprecipitation? All right. So please take note, this equilibrium is no longer present when it forms the deep blue solution. Can you recognize that? Because everything dissolved already, right? So this equilibrium is no longer existing. Yeah. So there's only two sources of one source of hydroxide, which is weak base. And this is what is existing in equilibrium together. Okay. So when I have H plus added, it will remove this OH minus. So when H plus remove the OH minus here, what does it do to your POE, to this one? Yeah, it will shift forward. When it shift forward, what will happen to this? It will decrease. And when it decreases, it will favor this part, right? When it favors this part, it will cause the ionic product of copper hydroxide to once again exceed Ksp. That's why you see reprecipitation of copper hydroxide. Okay, I give you 1 minute to digest this. Can I give you 1 minute to digest this? Okay, so in our inorganic QA, right, we call this a junction test. Yeah, it's a junction test. No. The H plus that is added, right, it will react OH minus away. So therefore, this will push forward.
How about this one?
This one, because you must recognize that the pale blue PPT has dissolved. The pale blue PPT has dissolved, right? Yeah. So the pale blue PPT which is dissolved, majority exists in this form.
Oh.
Yeah. So when the H plus is added, right, it will react this OH minus away. Then it will affect this ammonia.
Because less will be.
Yeah. So less is present, right? Then it will move back. Then this will go up again. So when this goes up, the ionic product of this will be exceeded. Yeah. Yeah. Okay. Can you discuss with each other what's happening? I mean, this is microscopically what's happening, okay, in your test tube. Microscopically. Can any questions to clarify for this part? Okay, so do you need me to do further explanation? So this is also the same case. Your excess of sodium hydroxide, it will favor the formation of this aluminate. So when you throw in a little bit of H plus, it will remove part of the OH minus from here. So therefore, it will shift back to partially offset this equilibrium, disturbance. Okay, so as you shift back, this will increase and it will favor the precipitation process again. Yeah. Okay? Is it okay? Yeah, so this is the reprecipitation process. Okay, let's try this checkpoint. Knock out already. Oh, already time. Sorry. Hey, yeah, we managed to finish. So in this case, right, checkpoint 6, sorry, can I just finish this part? So solubility will decrease in dilute hydrochloric acid. So with the very fact that it decreases the solubility, so what is the role of fluoride here? What's the role of fluoride here? Is it going to form a soluble complex or is it just exerting the common ion effect? Common ion effect. So you need to recognize the moment you are told that solubility decreases, the effect is just common ion effect. And please take note, you are not to answer, just say common ion effect, full stop. This is not correct. You must bring in the Chatelier principle. Okay, so with the okay, the answer is actually not very good. So please bring in the Chatelier principle. So in this case, please take note, the increase in chloride concentration due to dilute hydrochloric acid, okay, will be partially offset by shifting equilibrium 1 to the left, okay, favoring precipitation or less black chloride can dissolve. Okay, so you have to bring in the Chatelier principle. The recognition is common ion effect is there, all right? But explanation must be this. Okay, then for the next part, right, you discover that the solubility increases in concentrated HCl. Sorry, so this means that there's a formation of soluble complex. So the soluble complex form here is this. Okay, so you are following the same rule. The number of anion attached is twice the charge. So it's a lead 2 plus here. So there's 4 chloride attached. Okay, 2 plus charge here, 4 chloride attached. So because of this, right, concentration of cation decreases, therefore enhance solubility. So this is the Le Chatelier principle. Oh, okay. Yeah. Right. Thank you. Thank you very much for bearing with me. All right. The last bit I cannot go through. I'll go through the next time I see you. But you should be able to do your tutorial already. Yeah, tutorial will be due next week. So I will most probably discuss the tutorial with you on Wednesday. I see you on Wednesday, right? Nitrogen compound I'll continue on Monday. Yeah, I will finish that up. Then Ksp on Wednesday. Okay. In my Excel sheet, I think I put the more calculation part in front. Yeah, the rest will be following week. Okay, Ken?